Excellent. At least let's hope. Okay. I have no idea whether this is actually going to work. Anyway, welcome. So this is distributed systems. What I forgot actually to prepare is something that is something that we're trying to do every year, is to tell you how it went last year, how well we did. And it turns out that most of you will actually complain about the fact that this is so much. Now, some of you who have already taken this course know that I can do the math on the blackboard, and then you'll notice that it's actually very doable. So this is a 6 EC course, which means that you have to spend, on average, approximately 168 hours of studying, including class and including preparing for the exam. And if I would do the math on the blackboard, you'll notice that you'll actually have plenty of time to do your work. And don't show this message again. Nevertheless, hi, come on in. Nevertheless, it is a lot of material, and what I decided to do last year is actually switch from 2 lectures per week to 3 lectures per week. Now, what this means is that the pace during the lectures is going to be, well, I wouldn't say relaxed, but it's very, very doable. But I rely on you guys to actually do your homework. And I'm not going to assign any homework, but you just got to study the material. It's as simple as that. I have a very few principles. I will not tell you anything that is not in the book. I will not tell you any additional stuff that is not on the slides. Okay? And now I am recording these sessions, and well, you know, there's actually no reason for you to come at all. So that puts a challenge on me, because I always tell students I really like to see all of you come to class, okay? And don't worry, you'll be exhausted after my classes, but I'll be twice as exhausted if I could measure this. So what I am going to try to do is offer you added value by coming to these classes, and of course the added value is that I just stick to the principles. And I focus on the nasty stuff. So where all the other material on slides and in books is flat, everything's equally important, that's not the case in class. Okay, so that may be actually a good reason to come to class. There's another good reason to come to class. You get to ask questions. And in many cases, you actually get answers. Okay? And you actually get correct answers. Unless you have a very nasty question. And then I'll just... So I will do my best to actually make it worth your while to come into class. Okay? Because I love to have students in my class. Okay. Yeah, I think that's about it. So it's hard work. All of you will complain about the amount of material. If you take a look at the evaluations for this course, it's been I've been beaten by some people. Guillaume Pierre, who's a colleague of mine, he just became professor in Rennes, which will actually give me the opportunity to become #1 again. Okay, but he got 5s on all kinds of evaluations. But basically this course is very well evaluated, which generally means that at least your predecessors liked it, even if they failed for the exam. Okay, so it's remarkable, isn't it? So one way or the other, you will get the impression that despite that it's a lot of work, you will actually learn a lot. And that is, I guess, the job of me as a teacher. I have this gut feeling that I'm forgetting something, but we'll see. Okay? And like I said, it's an experiment with the recording. It should be non-intrusive, and what I'll try to do is to put the recordings directly on the site just after class. And maybe it's the next day, but it should be very shortly after. Okay. What are we going to do? We're going to talk about distributed systems. Oh yeah, okay. what's a distributed system? I hate definitions, but I'm going to try to give you a definition anyway. The whole course will be about talking about a collection of autonomous computing elements. Oh, I have to say a few words in just a minute. Autonomous computing elements that appear to users as a single coherent system. And the key word here is actually middleware. Oh, by the way, by using this gadget, I love gadgets, by the way. This is also now recorded. So you actually get a show. I mean, it's kind of nice. Now, if you look at this, it is a systems course, okay? And distributed systems really sit between, I think I should do this, between applications and operating systems. And what you'll notice is that distributed systems shield operating systems away. I mean, really doesn't matter whether this is Windows, this is Linux, Google Chrome, whatever. Those things would be irrelevant for, sorry about that. I always have to get used to this, yes. Irrelevant for distributed applications. And in this case, you actually see 3 applications, 2 of them on different computers, and 1 is actually spread across 2 different computers. Whoops. A distributed system hides the difference in operating systems and attempts to hide the differences in hardware. And in most cases actually does a reasonable job. Now, I just drew only 4 computers. That's not really a distributed system. The type of distributed systems that we'll be discussing consist of perhaps 3 or 4 when you're trying to introduce fault tolerance. This is a really nasty topic. And they can consist of 10,000s of computers when you just want to go for big numbers. Okay? Most of my research is about 10,000s of computers, actually. Okay, there's one deviation that I forgot to mention. If you take a look at either last year's slides or some parts in the book, you'll see that I'll be deviating. That's because I'm working on the 3rd edition of the Distributed Systems book. Nevertheless, I'll stick to the current edition, perhaps only deviating in chapter 8 when I talk about fault tolerance. And now I knew which slide I forgot, which is slide number 0. And slide number 0 is an outline of the course. I'm sorry that happens when you're looking at this train that's supposed to ride and didn't ride. So the whole course is indeed about the principles and paradigms of distributed systems. And what I'll be doing is I'll be mainly focusing on the principles and trying to explain those principles by means of examples. And one of those principles is fault tolerance, but we'll also be discussing communication, processes, synchronization, and more of those topics. In due time, I will also make a list available of the things that I think are important, okay? With double pluses and from time to time a minus. This is divided per section in the book. That will help you to actually study the material. So you don't have to study everything as hard. You could take a risk by just not studying some of the minuses. You're taking a bigger risk if you don't study the double pluses. Okay, it's as simple as that. Okay. There's something in. Oh yes. Oh. How stupid can I be? Some of you already did this, but I'm going to request all of you to do the following. You can enroll for this course. This is has nothing to do with officially enrolling it for Blackboard. I don't use Blackboard. I've had fights with Blackboard for years, and I just gave up. What you can do is if you just go to my site, and if you type my name, you'll find that site. There will be a drop-down menu for enrolling into this course, and the only thing that I will be doing is recording where you're from and your email address. Don't worry about it. I'm not going to use your email address for anything else but sending you mail on this course, okay? But it will also allow me to keep at least track of how many students are actually going to take exam, and it's also, if you want to ask me questions, just use that site. Enroll through that thing. If you do not get a mail back saying that you're enrolled, then something's wrong. And I'd like to know instantly. So last year something happened with another course, and it took a couple of days before somebody said, well, I didn't get a message back. But I need to know whether you get a message back to make sure that you actually enrolled for the course. You'll find on this site lots of material, including the slides and everything, and all in advance. Just go to the site. All the gory details are over there. Okay, and if you have questions, just ask me. Okay, let's continue with this one. Now, what are the goals of a distributed system? Well, there are basically only four. Making resources available, sure. Yeah, that's what all computer systems do. But more importantly is to hide everything that has to do with distribution. That's called distribution transparency. And then we have this obligatory stuff like be open and be scalable. Scalable is one of my hobbies. So I'll focus on distribution transparency and scalability. And I'll say a bit about openness. And making resources available, yeah, it's kind of obvious, isn't it? Now the distribution aspect and the transparency is actually a very important one. This has for a long time been the key element of distributed systems. And I'll already show you this one. Most of us actually gave up on distribution transparency because it's just plain hard. And sometimes it's not worth the effort. Now, what kind of transparencies can you talk about? One thing that we really master, I would say pretty well, is access transparency. And access transparency hides the differences in data representation and how an object is accessed. An object could be data. Okay, just think of a database or something like that. And for those familiar with object-oriented program, your object is your object in your Java or whatnot. We know how to do this. How many Java programmers are there in the room? Let me see some hands. Very good. How many people have been writing Java programs in a networked environment? A few. Okay. So what do you guys think about the access transparency in Java programs? Any opinions on this? Well, let me give you my opinion. I think it's pretty good. I think it's too good. The interesting thing about Java in a distributed environment is they have this notion of an object reference. And the interesting thing is you can't see the difference between a remote object reference and a local object reference, provided you do this right, okay? So basically, you don't know when you're invoking an object whether the object is on the same machine or on the other side of the world. And that's something I think, from a functional point of view, is pretty good. But what I will be explaining in just a minute is that when it comes to failures, it may actually be not so good. Okay? So access transparency, at least something, is what we managed to handle. Then there are three transparencies related to location. It's called location transparency, relocation transparency, and migration transparency. I think there's a mistake in the book. These slides are correct. Location transparency is hide where an object is located. URLs are a great mechanism for hiding the actual location of an object. Okay? And you can easily imagine. It's just in the name and you haven't the faintest clue apart from the fact that sometimes it's .uk or .eu or anything like that. But you don't know specifically where that thing is stored that you're referring to. Now, relocation transparency is the phenomenon that a system, a distributed system, may decide to move data or objects around without telling you. Okay? We'll be talking about cloud computing. And what happens in the cloud, is just another distributed system, is that for all kinds of optimization reasons, the system will decide to move data around. Okay? But you will not notice it. That's relocation transparency. We know how to do this. Then there's migration transparency, and that's the transparency that an object will decide to move to another location, and it will not tell you. So what's the canonical example of migration transparency? You all know this. Yes?
If, for example, we
Whoa. I guess the answer is good, but I know a much simpler answer.
Virtual machines?
Oh, I love this. It's also good, but there's an easier one. What? No. This is, one thing that this morning I actually taught some things about cloud computing to MBA students. I mean, they're not techie guys, right? And I don't know exactly what question I asked. I was getting all these deep technical answers. They didn't really know what they were talking about. They don't understand the technology. But I was thinking, hey, my God, this is an answer that's so easy. And in your case, it's also very easy. Just think out of the box. Forget about distributed systems. And now you talk about migration transparency. And you read that definition. Hide that an object may move to another location. Or being called, or whatever. Your smartphones, okay? When you call, this was for a long time the biggest application for a smartphone. It was a very simple application. Where are you? Okay? Because the telephone is not going to tell you. So it's a good example. It's the obvious example of migration transparency. You move, you don't inform anybody, and that's it. And nobody's supposed to know because they just want to get you on the phone. Okay? I will be asking you guys many of these type of questions, okay? And then in many cases, don't go for the obvious. So the other answers were okay, but often it's simpler. So virtual machines can move, and deep in the system and moving bits. Hey, a smartphone, that's migration transparency. Yes?
So we can say the smartphone for the verification transparency also. I don't realize many difference between.
Yeah, it's from time to time I'll be repeating the question just to record the question. Okay, so what is now the real difference between migration transparency and relocation transparency? Because this is, I think I understood from your question, it's very subtle. And there's actually a subtle difference which is essential. In migration transparency, you decide to move. Okay? So if you're a program, if you're a smartphone, you decide to move, and that movement is hidden from anybody who's dependent on you.
So by the object, you mean the user?
No, the objects can be your smartphone, can be your data, but it is, for example, the program that is manipulating the data that says, I will move to a different location with my data. In that sense, the smartphone is a good example. Relocation transparency is that the distributed system, who is controlling data placement, decides, I'm going to place that piece of data somewhere else because, for example, this happens in the clouds, then I can spin down the disk that data is stored on and still make it accessible. Okay, so if you think of data centers, if they want to save on energy, they actually migrate not just the data, but also the virtual machines so that they can shut down certain servers. That's relocation transparency. Okay? And even if you're the object, you have no say in this. Yes?
That brings me to another question. In this case, in my opinion, the smartphone example is more a relocation than a migration because the server eventually decides that the smartphone is moving, so it has a better signal in another point, so I will just make him access the other point, etc. So the server decides that the smartphone
one thing is, my God, it's already popping up very, very quickly. One of the nasty things in distributed systems is that there's no single good answer. So I like your reasoning. If you would write this up for your exam, you'll probably get lots of brownie points for it. Okay, because it's not wrong. And what I like about your answer is that you give argumentation. So the argumentation here is like, the argument is like, hey, it's relocation transparency because the server will conclude that something is moving and decide blah, 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 to move other things as well. I would still argue that smartphones are more migration transparency than relocation transparency because it's the owner of the data that actually makes the movement. But hey, it's a thin line. I agree. Which means, also as a general example, if you write up an answer during the exam and the answer is yes or no, I may be in the habit, depending on what time of day it is that I'm grading these exams, to say, go away. I'm not interested in yes, no answers unless I explicitly ask for that. I'm interested in yes, because, or no, because. And it's really the because that really counts, okay? So watch out for that. So you would get a lot of points for this, whether I agree or not, okay? That's
But not
yes.
come to this point.
What?
But not come to this point.
Well, it depends on how I phrase the question. For the access transparency, I can give you lots of examples. One is with Java programming. Another one that's pretty good is database access over networks. You often do this by a simple SQL interface. Okay? And another one that we'll be discussing at length is called a remote method invocation, or a remote procedure call. And notably the remote procedure call, it will show that it's not a black and white answer, yet pure yes or no access transparency. It's a line. Certain aspects can be hidden and certain aspects cannot be hidden. But don't worry, this is only the introduction. We'll be talking at length about replication, not in the last place because it's really a fun topic. There's a whole chapter on replication, and fault tolerance is mostly also about replication. That makes 2 chapters. Now, the nasty thing about replication is that you really want to hide that data or objects are replicated. And we need replication for fault tolerance, and we need replication for performance. Okay? We'll come back to that at length. Concurrency transparency is almost an obvious one. It basically tells you, hey, I have a distributed system, it's for lots of folks, and I just don't want to know about the others. Okay? So when you are working on your distributed system, you don't want to be bothered by the fact that there's someone else out there who's also doing a transaction. That's none of your business. That's called concurrency transparency. And in most of the cases, it's so obvious that we actually forget it. Okay? But this is what you do in distributed systems. Now here's a nasty one. Failure transparency. Now one of the really tough things about any networked system is that, and notably the big ones, is that there will always be something wrong, okay? But the system will not go down entirely. And for those who were on the local network this weekend, they noticed what was happening. Parts of the network were accessible and other parts were not. And not only that, it was totally unpredictable when you can actually access your mail, for example. So to give you an idea, what I personally do is I have a mail server running on my desktop, and it fetches mail from the mail server at the VU. Okay? So what I'm doing is when the network actually came up, my fetch mail program fetched the mail, and hey, my mailbox was there, right? So I didn't notice that something was wrong until the point that I couldn't reach my desktop. So something fishy is going on, and I don't know exactly what. So people were saying, hey, it's about the services, and I was noticing, hey, the network's not working. Sometimes it is, and sometimes it's not, and I don't even know which part. Now, this is an inherent feature of any distributed system. It never, most of the time it just stays up and running, but there's always a part that doesn't work, and you don't know which part. And not only that, it may be that you think it's that part that's not running, but the fault is over here. So every year, when I talk about distributed systems, I characterize them by this. You push here, and it hurts over there. And this is something that will happen over and over again. And when you just go for the symptoms, it's hurting over here, it may not be enough. You have to try to find out what the real cause is of why this failure happened, or any failure, or and a failure sometimes comes up as a performance issue. It's not working as it used to be. What is going on? Now the problem here is that in a distributed system you try to hide these failures and the recovery from those failures. The point is that you really want to recover from the failures. This is, by the way, not obvious. Sometimes when you have a failure, you don't recover from that failure, you just do something else. Like, if you're Google, you just throw in a new PC. That could also be recovery. Theory, however, tells us that you cannot go for full failure transparency. It is theoretically and practically impossible to fully hide failures and the recovery from failures. Welcome to distributed systems. Now you have to realize what this means when you're an application developer. If you develop a distributed application and you do not take into account that the system will let you down, you're writing the wrong application. You have this obligation to throw in these rules for handling exceptions, and the exceptions will be related to failures in the distributed system, most often caused by communication or server failures. Okay? You have this obligation. This is unique compared to standalone applications, which hardly ever exist, by the way. Because what happens in the standalone application, if it fails, well, you know, your whole computer will fail. And that's good. That may sound strange, but it's actually good. And what you do is you reboot this stuff and it actually works again. But you can't do this in a distributed system. You can't reboot a distributed system. That thing will just go on and on and on and on. Try shutting down the internet. It's not going to work. So you have to take into account that there will be failures, and sometimes you will notice as application developer. And there's no way that you can cover those, mask those failures, so you will have to do something when you can't handle that failure anymore, and the only thing you can do is tell your user, hey, something went wrong, what do you want me to do? Continue? I think it was just on the screen, right? You want me to continue? Well, no. So that's something you have to realize. This is a characteristic feature of distributed systems and distributed applications. Okay. There's a whole chapter on fault tolerance, so you can imagine that we'll pay some attention to that. Now, actually, I mentioned a lot of these things. Aiming for full distribution transparency may not always be a good idea. An obvious one, if you have a big distributed system, the users may actually be located in different continents, living in different time zones. It's generally okay to take that into account, okay? But like I just mentioned, completely hiding failures is theoretically impossible. And what we'll be talking about is that, in general, you cannot distinguish a slow computer from a failing one. Okay? Because basically what you'll have to do is, if you decide that you haven't got a response after 10 seconds, well, what do you want to do? You want to give up? Sure, that may be a good decision. But do you know for sure that you're giving up because the server is down or that the communication with the server is down? And the fact is, you can't tell. Because the only thing that you have is a message that didn't come back. There you go. So you can't hide it. And this is also a very nasty one. You can never be sure that a server actually performed an operation before it crashed. Okay? So even if you knew, even if you got a message from the server back saying, hey, I just crashed, that server is in the general case not able to tell you whether it had already performed the operation that you just sent or that it didn't. And you have to take this into account. We'll be talking about this when we talk about so-called idempotent operations. This is an important one. Full transparency will generally cost performance. Okay? And here you have it. I was just saying you push here and hurts over there. Here's another thing that you'll have to do in distributed systems. There's never a good solution. So you have all these knobs out there. Now what's the optimal setting of knobs? Well, if you turn this knob a bit like this, performance will go up, but hey, your reliability will go down. Oh shit. Okay, so let's increase reliability, and then suddenly performance goes down. So what's better? I don't know. Depends on the context. And this is something that is unique to distributed systems, or actually any networked system. You will have to decide under which circumstances you turn this knob up or down. And like I said, there's no single solution. And this, I think, makes this topic or even course so fun. You got to think. Okay? You actually really have to think, what would I do? What is a good trade-off? And this whole thing is about making trade-offs. And the better you understand distributed systems, the better the trade-offs are that you can make. And the people here who really have this sixth sense for distributed systems, they will instantly understand under which circumstances they should do A or B or C or the rest of the alphabet. Okay. Here are some examples, but we'll come to those later on. Oh, no, okay. No, this is just as a side effect. Flushing write operations to disk. Years ago, I was working on a system, and we'll be discussing it briefly somewhere down the road, on a location service. And the interesting thing was that we were looking at storing mappings between random identifiers and actually, I'll just keep it simple, IP addresses. And you know that the whole performance of that system was not dictated by our communication, but in the end was dictated by the time it took to write operations to disk. And we needed that for reliability, and it turned out that that was actually our bottleneck, not the communication over the internet. So it's interesting to see how you would deal with that. I don't think it's going to be an issue anymore because you would probably just store this on fast memory, like a flash or something like that. But still, it illustrates how something really mundane, like write operations on a disk, can actually dictate the whole performance chain in a distributed system. And it makes you think, and it makes you think in terms of trade-offs. What do I do? And again, there's no obvious solution. Okay. Openness of distributed systems. Most of you already have taken courses in software engineering, right? And so basically you know this. When you write software, it has to be good, it has to be open, it should be able to interoperate with other pieces of software. You don't write a standalone program and blah, blah, blah. So systems should conform to well-defined interfaces. Systems should support portability of applications. Very good. And systems should easily interoperate. Very good. And what happens in practice is they do have well-defined interfaces, millions of them. Portability is pretty good, actually. I think we've managed to handle that. Interoperate? Nah, not really. When you go out there in practice and you talk to people from IT departments in big companies, they will tell you that one of their major problems is tying up these legacy applications to each other. And legacy applications is talking about how do I make my legacy systems, applications, interoperate. And there are companies who are making big business out of that, just coupling legacy systems, and they just don't interoperate. Now, when it comes to distributed systems, how do you achieve openness? Well, at least we can make systems independent of from the heterogeneity of the underlying environments. So, yes, hardware, platforms, operating systems, languages, we can handle that. If there are people over here who think that you program a system in one single language or that there's one really terrific programming language, sorry, real-world systems are built from a gazillion languages. Scripting languages, C, C++, Java, declarative languages. They're all just hacked together in a software engineering fashion. And even that is, by the way, changing. But we can handle that. That's not where the difficulties come from. Okay. Now this is also, actually this is pretty good. Policies versus mechanism. I'll show the whole slide first. Now, policies versus mechanisms is something that those of you who've taken a course in operating systems understand. So if you take a look at an operating system, what an operating system is supposed to do is to make your life easy. And making your life easy also consists of giving you control. Okay? So a good operating system comes with a lot of knobs to make sure that you can fine-tune the operating system to the needs of a suite of applications that will be running on top of that operating system on top of that machine. Okay? And these knobs come in the form of all kinds of runtime configurations, but they can also be compile time configurations. Okay. But here's the snag. Oh, by the way, and distributed systems do exactly the same thing. They give you lots of knobs. Why? Because the general idea is that a distributed system or any system software should not dictate how you use the resources. Okay? It should not dictate that you are allowed to have only 4 gigabytes of memory for your cache to temporarily store things. Or it should not dictate what kind of trust you should put into mobile code. Mobile code, for example, is the stuff that you fetch from a server and that you run in your browser. Okay? Those are all policy decisions. It's up to you to decide about trust levels or sizes of caches or whatnot. And here's another one, your choice of encryption algorithms. Many of you actually know this. You know, there are applications that, where you can store your passwords in databases. Hey, what kind of encryption scheme do you want? I have 12 things to choose from. Now the drawback, so that's generally good, okay? Separating policies from mechanisms. Now the drawback of this separation is the fact that your distributed system may actually be overwhelming. It may be just too intricate. And what happens is that you get a bunch of default policies. Okay? And everybody just goes for that. That happens in practice. Now, imagine the following trade-off. Suppose you would not offer lots of mechanisms that will allow you to support many different policies, of which a few would appear to be reasonable and which you would offer as a default, but instead you would hard code policies into your distributed system. You make the choices. What do you think would happen with your... If you would have to program, develop a distributed system, what do you think would happen to your code if you decided to hard code policies? Would it be good? Would it be bad? Let's hear some things. Now from the developer's perspective. From the developer's perspective. It's quite okay. What do you mean by quite okay? Your boss wouldn't be happy. Well, maybe your boss would be happy.
You can fetch all or you're pretty sure that a certain amount of data has been input in a certain way, so you can fetch all the other stuff.
So how would you see a hard-coded policy in a distributed system? What would it look like? Can you build a picture of that?
It only allows for certain kind of characters to be input.
Exactly. Okay, so you're really confining the user to specific things. What it really means also is that your code becomes simpler. So your boss will be very happy because you're making a decision for a policy, you're actually often, not a general rule, making code much simpler. Because the code is much simpler, your system is easier to maintain. It's also much easier to prevent things going wrong. Okay? So here you have an interesting trade-off. If you hard code policies, and later down the road I'll show you an example of a system called ICE, which has hard-coded policies. And the thing about systems like that, like ICE, is that you can read the code and understand what's going on. Okay? If you would take a generic system, and just take any operating system for that matter, and if you would then try to understand what that system is doing by looking at the code, that will be an interesting piece of homework. Okay? It's just difficult because there are so many options. And they did this for a good reason, because they were implementing mechanisms and not policies. So here you go. Welcome to the world of distributed systems. Make a trade-off between hard coding policies versus offering lots of mechanisms and flexibility. And well, you know what I'm going to say. There's not a single good answer. Okay? And the only thing I'll be telling you all the time is, hey, this is what happens when you fix the policies, meaning no flexibility, if I exaggerate a bit. And this is what you get when you fix no policy but only concentrate on mechanisms. Hey, lots of flexibility, but hey, the price to pay is perhaps an unmaintainable or difficult to maintain system. Your choice. Okay? And is the truth somewhere in the middle? Probably. But it all depends. Depends on how you're going to use these things. Okay. What time are we in? Okay. I'm going to continue just a bit longer. Okay? The class stops at 3:15. I'm going to try to stop at 3:15. But could you bear with me just a bit longer? I hope so. Okay? Don't worry. I'm just trying to make your life easy, actually. Now, I want to talk a bit about scale and distributed systems. And after this, we can actually speed things up a bit. Many developers of modern distributed systems easily use the adjective scalable without making clear why their system actually scales. And I know it's very warm in this room, but now you really need to pay attention because this is a crucial thing in distributed systems. Now, when you think about scalability, there are at least three components. You can talk about size scalability, geographical scalability, and administrative scalability. And what most vendors will actually do is they will talk about size scalability. This is what's on this observation here. And size scalability is easy. Size scalability means, hey, I can have lots of users. And the real solution to size scalability is throw hardware. Throw bigger machines, okay? More main memory. It's not entirely true, because if you have a system that was not really distributed and that has to scale up because of users, and now you have to move it into the cloud, but you need so much memory that it actually makes sense to have multiple servers running in parallel in that cloud, you do have a big scalability problem, because you have to turn your single machine system to a multiple machine system. That's not always so obvious to do. But in general, throw money, you got yourself a solution. Okay? So the challenges actually lie in geographical and administrative scalability. Now watch this. First, let's take a look at how you can actually scale. Okay, what kind of scaling techniques are there? So now just think big. Think really big. 10,000s of computers, network system across the internet, and now Mother Nature is going to get in your way. So one thing that Mother Nature is going to do is going to say, hey, it's going to take me hundreds of milliseconds to get a message from here to there. Here it could be Amsterdam, there it could be Hawaii. Okay, other side of the world. And Mother Nature is just going to say, well, that's it. Nothing you can do about it. You got to solve it. Okay? And there are a couple of things you can do. So you have to realize that hundreds of milliseconds need not necessarily be a problem, but if you have an interactive application, it is a problem. And also the example that actually I gave this morning to the MBA folks was the following. Years ago, I got this example from somebody working at IBM, and the bottom line was they had this information system roughly consisting of a front end and a back end. The back end was the database, and it was running in Rotterdam. And what happened was that they decided to move the back end to Hungary. Okay, so far so good. So we had the front end in Rotterdam, and we had the back end I think it was in Budapest indeed. And the network provider could only give guarantees for pretty lousy latency requirements between Rotterdam and Budapest. I think it was in the order of 160 milliseconds. That was the deal this provider was willing to make with IBM. Now, unfortunately, the front end was talking to the back end like this. Done. Done. And every time I do this, there's communication between the front end and the back end. And this will not be recorded now by video, so I'm waving my hand, okay, just to give you context. Sorry, I have to get used to this as well. So now imagine that the back end is now placed in Budapest and you're over here in Rotterdam. Well, you can't do this anymore, waving hand very quickly. What you can only do is, okay, now I've just landed my message in Budapest. Now I come back to Rotterdam for a response. Go back to Budapest for the next part of the message. So suddenly, by design of the interaction between the front end and the back end, you've just introduced considerable delays up to the extent that it's not acceptable anymore. And you know what the really bad news is? So what's the bad news here, actually? It's very difficult to change. You said that? Absolutely correct. You have to redesign the interaction between the front end and the back end, which can be a major effort. There's no way that you can throw in hardware or anything like that to circumvent the problem. You've got to solve it. Okay? So there are cases where you just don't have a choice. Well, in the case of communication latencies, you may be in good luck by redesigning the interaction to make sure that it makes use of asynchronous communication. Okay? So basically you send something out there, so the message is now on its way to Budapest, and fortunately, you have something else to do. Okay? If you can afford that pattern, what you can then do is essentially have a separate handler for incoming messages. You spawn a thread or a process saying, hey, wait until you get the message back and then wake me up again. Okay? But the problem, of course, is that not every application fits this model. Email fits this model perfectly well, except for the impatient. Another one that is generally applied and that you all know is simply distribution. By that I mean just spreading things around, okay? And the best example that I always come up with, I think, is the World Wide Web. This is a huge information system. It is, I always forget the number, but I think there are, okay, I'll just throw up a number, but I don't know if it's correct. 160 million web servers. I think it's more. Can you imagine how many? That's a lot, okay? And the whole system just works. Well, what does that mean, just works? Well, you know, you get your information. If you can find it, you'll get it. And it scales up to these numbers because all these pieces of information are just spread across the internet. So this is a very good example of scaling up a system by just distributing the load and the data and whatever across millions of servers. And we'll talk about other ones as well, like DNS has exactly the same, but also using Java applets is actually a very interesting way of distributing the load. I, as a server, am not going to do anything, but hey, you as a web browser running on the client side, do your work, okay? And finally, a very important one is replication and caching. Well, there's often a difference. People make a difference between replication and caching. I'll make that difference from time to time as well, but there's no fundamental difference. The end effect is you make copies. Okay? And you see replication, mainly just copies of data, by servers and databases. Mirrored websites, we all know this phenomenon. Web caches, and there are a gazillion web caches out there. And file caching. Okay. Oops. Let's see if this can work. Okay. Now, before I continue with this, I will allow you to have a break. Okay. And let's take a 10-minute break then. Okay.
Last part van die Rotterdam en is het niet voor wat sliding window, dat niet een goede oplossing zijn voor dit probleem?
Nou, het zou kunnen, maar wat je dan eigenlijk introduceert is asynchrone communicatie. Wat je dan zegt is... Nou ja, waar het om gaat is, op applicatieniveau stuur jij een bericht. Oh, wacht, misschien moet deze...